Hey, hello world. How's it going out there? What a fun thing to be doing today. Kirill, thank you for running through all of those stats. I enjoyed going through those. It is such a nice target audience that you've put together here. Happy Father's Day to those dads out there. It's a very bright, sunny day here. I'm in northern New Jersey, and we got the air conditioning blasting so that I can stay cool as I give you this presentation. So I'm going to share my screen. We might as well dig right into the content. So am I? Perfect. Sharing screen, whole screen. Here we go. Nice. So let me full screen the talk. There you go. Welcome. This lecture is called Deep Learning Model Architectures for Natural Language Processing. My name is Jon Krohn. There are two resources in the bottom left-hand corner here that are going to make life easy for you for following along with today's talk. So let's go to the first one, which is jonkrohn.com/talks. So if you go to jonkrohn.com/talks, you will find yourself at this page where there's a photo of me in a pre-COVID world where look at all these people so close together giving each other various infections. And the important thing here is today's lecture. So I have, for today's lecture, you can download the slides as well as access. There's a link here to the GitHub repository that I'm using for the code. And so if you click on slides, you'll find yourself literally right in here where I am. I can see some people have already done it. I'm joined by an anonymous giraffe, an anonymous war. What do we got in here? A raccoon just joined. Fun to have you all in here. Loads of people piling in. So that's the first link that I want to draw your attention to. And you can download these slides in any format you want. So you can go to File and then Download, and you can download as PowerPoint or PDF or whatever takes your fancy onto your local machine. Or you can just stay in the web browser. The other link here is the GitHub repository. So github.com/JonKrohn/DLTFPT, which stands for Deep Learning with TensorFlow and PyTorch. That also, if you're on the talks page already, the code link will take you to that same page. Here's what that page looks like. The page, it is from a set of videos that I created that I released earlier this year in February and March. So it's 18 hours of video content. The first 7 hours is here, and that covers an introduction to all of deep learning and the main libraries for using it. The second video is a 5-hour video on deep learning for natural language processing. And the content that we're covering in today's class is what I thought would be the most exciting hour from that 5 hours of content. I've summarized it down into some specific slides, distilled it down to the best parts. If you want to follow on to anything deeper from today's lecture, then you might want to check out these videos as I will go into way more detail. So in here, the main reason why we're here is because there's tons of Jupyter notebooks. So we're going to be using Jupyter notebooks from in here. When we actually get to that point in the talk, I'll pop in and we can start working on them. But I wanted you to be aware already right at the beginning of what all of the resources are. So let's move into some content, and then we'll return to some hands-on code demos, and we'll use Google Colab so that you can participate during class time. So there are 3 segments to today's talk. The first is called The Power and Elegance of Deep Learning for NLP, in which I will introduce how deep learning is such a powerful approach to tackling natural language problems. In the second part, we'll get into our first hands-on code demo, where we will use some sort of well-known deep learning architectures, dense networks, convolutional neural networks, to tackle a natural language processing task. And then in the third part, I will introduce you to recurrent and advanced neural networks, including transformer architectures. Lots of people talking about architectures like BERT and GPT-2 these days, and we will talk about those too. So let's start off with the first section, the power and elegance of deep learning for NLP. Of course, there are two core concepts in today's lecture, so let's tackle them one by one. The first is deep learning. The second is natural language processing. So I'll just spend a slide explaining what each of these are for those who aren't familiar. So in a single slide, the way that I most like to talk about deep learning is to distinguish it against the other kinds of machine learning approaches out there. So regression, support vector machines, decision trees, including random forests, I tend to clump those together into what I call traditional machine learning. And with those traditional machine learning approaches, a practitioner spends the vast majority of their time, maybe 80 or 90% of their time, engineering features out of the raw data. So if you're working with natural language data, this could be raw text. It could be audio waveforms. And in a traditional machine learning approach, you would spend the vast majority of your time writing functions to extract meaningful information out of the vast amount of raw natural language data. And so you might spend a very small amount of your time, 10 or 20% of your time, actually flowing those processed data through models which might be relatively simplistic, regression or support vector machine models. And in contrast, deep learning turns that whole idea on its head. So with deep learning, you might spend 10 or 20% of your time, or maybe 0% of your time, engineering features out of the raw data. Instead, you spend the vast majority of your time actually training your model and devising new model architectures. The powerful, incredible thing about this idea is that it means that you no longer need to be a linguist. You don't need to do a PhD in the specifics of how language is structured in English and then maybe some other language that you want to build a machine translation tool for. So we're talking about 5-10 years of expertise development in the traditional machine learning approach to build a state-of-the-art model. In deep learning, we can rely on the model architectures primarily and maybe have minimal experience in language itself or the particulars of your natural language problem and still build a very powerful, maybe approaching state-of-the-art model. Okay, so this is a really cool thing. So that's a very quick introduction to deep learning. The second core concept in today's lecture is natural language processing. So what is that specifically? It is a field of research that sits at the intersection of computer science, linguistics, and artificial intelligence. If you have a deep interest in natural language processing, I definitely recommend checking out that 5 hours of video that I created because it will provide a thorough introduction to everything around natural language processing. In today's lecture, we're going to have to skip over some of the basics in order to jump to the more exciting stuff where we're actually building models hands-on. To get everyone up to speed, however, I wanted to at least talk about vector representations of words. So these are called word vectors or word embeddings, and these word embeddings are a quantitative representation of the meaning of words. So tools out there that you may have heard of for creating a word vector space include tools like Word2Vec and Glove, Fast Text. These are all approaches for creating a high-dimensional space where every unique word in your training data gets assigned to a location in this space that represents the meaning of that word. So we might have, up in the top right-hand corner here, we might have various time-related words. So we might have a cluster of words in orange, Monday, Tuesday, Wednesday. And then nearby in purple, we might have months of the year, January, February, March, April. Then in a completely different part of our word vector space, we might have programming languages. So we might have object-oriented programming languages like Java, C++, and Python forming one cluster. And then nearby, another cluster of functional programming languages like Haskell, Clojure, and Erlang. So the way that these models work, whether we're talking about Word2Vec or Glove or Fast Text, they put words in more similar locations if they have much more similar meaning. So common misspellings of words, the British or the American spelling, they will end up in effectively the exact same location because they get used in the exact same context. And synonyms will show up nearby. Related words obviously will show up nearby, as in the examples that I just showed of these particular clusters. In this visual representation of a word vector space, I've drawn it in 3 dimensions because our feeble human brains can really only handle visualizing things in 3D. However, in practice, you would typically train this space to have a 32 dimensional space, or 64 or 128 dimensions. I tend to vary by powers of 2 when I'm creating it, and it's a hyperparameter that is specific to your particular problem. Effectively, the more dimensions you have, if you double your number of dimensions from 64 to 128, this can only improve the accuracy of your downstream natural language task. However, that simultaneously doubles the amount of computational requirements. So there's this trade-off, some kind of Goldilocks sweet spot between accuracy and performance that you want to hit in deciding on the hyperparameter for how many dimensions you have in this space. So if you ended up choosing a 64-dimensional space, then say a word like king, it would have a 64 length vector that would describe its location in this 64-dimensional space. Because this is just a 3-dimensional little representation, we can represent the location of king simply with an x, a y, and a z coordinate. Now, I've explained one of the really powerful things about a word vector space, which is that location corresponds to meaning. However, an even trippier property about these word vector spaces is that particular directions and distances through these space correspond to meaningful, real-world meaning, translation between words. So it's easiest for me to explain with an example. So if you take the direction and distance between the words man and woman, this particular vector from this point to this point, that same direction and distance also separates uncle and aunt, king and queen, and so on. So this is a really trippy thing that ends up happening. It ends up just being the most efficient way for the algorithms that create these word vector spaces to represent the data. As a second example here, I have cities and the country that they're capital of. So you'd have a particular direction and distance that represents the difference between London and England, and that same direction and distance would correspond to the direction and distance between Paris and France. And so this allows you to do actually word vector arithmetic in kind of a fun way. So if we take that particular location that represents the word king, in our example on the preceding slide, that was a 3-dimensional vector representing the XYZ coordinates of this word, but this could be in a 64-dimensional space. You'd have a 64-length vector describing the location of the word king. Then you can subtract the location of the word man, add the location of the word woman, and you would find yourself in a well-trained space at the vector that represents the word queen. Isn't that crazy? If you haven't come across this before, I hope you find that mind-blowing. And I certainly did when I first discovered this. And it's really fun to play around with kind of your own arithmetic in here. So some other examples I've seen: Bezos minus Amazon plus Tesla, we end up at Musk. Windows minus Microsoft plus Google, we find ourselves at the word Android. And then for you chemistry nerds out there, if you remember your periodic table, here's a fun one down at the bottom with copper and gold. So if you want to dig into all of this content in more detail, everything I've just explained a little bit about the basics of how we represent language, as well as anything else related to deep learning, I do recommend checking out my textbook, Deep Learning Illustrated. And in this book, in particularly chapters 2 and 11, we focus on the content from today's lecture, but we can dive in a lot more deeply, obviously, in the book than in today's class. And so just to give you a sense of the kind of things that I'm not going to have time to explain in today's class in much detail related to deep learning, that I just have to kind of assume you know. And if you don't know these things, it's okay. The lecture will still mostly make sense. There's just going to be some parts that you need to take my word that this is how things work. And you can come back to the book later and you can fill in the blanks. So some of this theory assumed is what artificial neurons are. So an artificial neuron, it's the fundamental computational unit of an artificial neural network, including a deep learning neural network. Cost functions, these are common across machine learning, so hopefully you've come across them somewhere. So cost functions give you a way to quantify how incorrect your model is on any given slice of data provided to it. Stochastic gradient descent is, again, a popular machine learning technique that we will be using in today's class to reduce cost. So cost gives us a sense of how wrong we are, and then we will use stochastic gradient descent to adjust all of the parameters, what are called the weights and the biases of the artificial neurons that make up our deep learning network. And this will allow us to reduce the cost, and our network will be able to perform the task that we're training it to on the data that we're providing it. I'm also assuming that you know what dense and convolutional layers are. So these are specific ways that artificial neurons are connected to each other. So a deep learning network, it has at least 5 layers of artificial neurons, and some of the most popular layer types are these dense and convolutional layers. So a dense layer simply receives an input from all of the neurons in the preceding layer. So it's relatively simplistic, but also very powerful because it's capable of recombining anything from the previous layer. And convolutional layers are another layer. They're most common in machine vision. They're capable of identifying spatial patterns, and so they're great in machine vision for identifying 2x2 or 3x3 windows of pixels that represent a particular spatial pattern. But we will use them today to detect patterns of words. And another key thing about deep learning that I should just say here, in case you're somebody that isn't aware of how deep learning works, is when I say that a deep learning architecture has many layers, as we go from the input, so we input our, in today's examples, we'll be classifying the sentiment of movie reviews. So we have a movie review data set where we have 25,000 movie reviews. Half of those are positive reviews, half of them are negative reviews. We're going to feed the natural language of those reviews in at one end, into the input end of our deep learning architecture. And then we're going to use the architecture to guess, to output a guess as to whether a given movie review is a positive one or a negative one. And as we go through the layers of our deep learning architecture, the representations will become increasingly complex and increasingly abstract. And so that's just another important aspect that I want to make sure you're aware of. And so these dense or convolutional layers, the early ones identify simple patterns, later ones identify more complex patterns. Pooling layers allow us to reduce the computational complexity of our model. Basically, we'll be using them to say, okay, if I have a pattern of words, I don't care where that pattern occurs in the movie review, just that it occurred at all. And then dropout is a technique where we randomly remove some proportion of the neurons in the model architecture. And this prevents the model architecture from overfitting to our training data. And so our model generalizes better to data that it hasn't seen before. And if you want the book, you can get it 35% off orders at this link here. You can use code Krohn during checkout. Although I believe my publisher Pearson provided DataScienceGO provided you guys with a 40% off coupon, as well as a 60% off coupon for videos. I don't know the codes for that, but hopefully it's easy to find somewhere in the DataScienceGO materials. Okay, so that's the first section. That gives us a quick introduction to the power and elegance of deep learning applied to natural language processing. In the second section here, we're going to actually start jumping hands-on into modeling natural language data. And we're going to start off by using a dense neural network, and we're going to do that to solve the movie review classification problem that I described a moment ago. So let me go to my, wow, there's a lot of people in the slides now. 79 of you, welcome. So we'll make our way over to the Github repository. For those of you who missed it from earlier, it's github.com/Jon Krohn/DLTFPT, and you can access that from jonkrohn.com/talks. There is a code link here, and so that will bring you through to this deep learning with TensorFlow, Keras, and PyTorch repository. So if you are familiar with running Jupyter notebooks inside of a Docker container, then there's a Dockerfile here that you can use to ensure that you have exactly the requirements that we need for running all of the code in this repository. If you're unfamiliar with doing that, I wouldn't recommend doing it right now because we don't have time, but on your own time, if you're unfamiliar with running Jupyter notebooks inside of Docker containers, it's a really nice way to ensure that you have all of the software dependencies you need without impacting other software on your system. And so I have installation instructions here for Mac OS, Unix, and Windows, and you can follow those step by step and get set up. But I wouldn't recommend doing that right now. Instead, for now, since we only have 19 minutes left in class, I have a much quicker way of running these notebooks, which is simply by selecting the appropriate notebook. The first one that we're starting with is called Dense Sentiment Classifier. So click on Dense Sentiment Classifier, and that will bring you into that Jupyter notebook. And I provided a very convenient Open in Collab button at the top. So you can click on Open in Collab, and this will bring you to the Google Colab environment, which provides you with a Jupyter notebook in a Google Cloud computing center that is relatively close to you. And all that you need to access this, actually you can access it, you can view things statically in here for absolutely nothing, with absolutely no work. You can just go to the URL. And if you want to execute the code interactively, all you need is a Google login, and it's free. So, your Gmail login or whatever you can use to log in. There are some of the cool things about being in Collab is that it comes preloaded with lots of the software dependencies that you need in data science and in machine learning. One of the downsides is that then you don't have control over the specific versions. So someday I'm going to be giving a demo, and I'm going to have a serious error thrown. Hopefully today's not that day. So that's one of the advantages of doing things on your local machine. The other advantage of doing things on your local machine is that you can let a model train indefinitely. Whereas in Google Colab, after half an hour of not interacting with your Jupyter notebook, you'll get thrown out of the session. So those are some of the pros and cons. And the final pro that I want to tell you about Google Colab is that this cloud instance that you're using is pretty beefy. I guarantee it's way beefier than whatever you've got on your laptop. And you can go into this runtime button, and you can change runtime type. And for some kinds of deep learning models, not the ones we're doing today, at least certainly not this first notebook, you could change your hardware accelerator to GPU. So if you're doing a machine vision task, using a convolutional neural network for that task, selecting a GPU you might get a 10 times speed up on training your model. And in most cases, that's going to be way better than what you could be doing on your laptop. For this notebook, though, we can just leave hardware accelerator on none, which means that we will use CPUs only, 8 of them, I believe, in almost all cases. One other final thing I'd like you to do before we get started in this notebook is to click on Edit and clear all outputs at the bottom. So we had a completely executed Jupyter notebook in GitHub where you can see all of the code executed and printed out, and lots of charts and that kind of stuff. By clicking on Edit and Clear All Outputs, we clear all those outputs and we create them ourselves as we work through this tutorial right now. So the first cell here is loading our dependencies. We're working with TensorFlow. That's our automatic differentiation library that we are using to train our models. And we are specifically using its Keras module, which allows us to very quickly build powerful state-of-the-art TensorFlow models in the back end. It's a good practice, whether you're writing code for yourself or for your colleagues, particularly if you're doing it for your colleagues, to have all of your model hyperparameters listed in a cell at the top of the file. So, for example, I have an output directory here where we're going to save out our models after every epoch of training. How many epochs of training we're going to be training for. So we're going to go 4 times over all of the training data that are in our training data set. Batch size, so how many movie reviews will we be including in a round of gradient descent. And this is a hyperparameter that I've tuned. I don't recommend going higher than 128. 128 will typically be the one that takes the best advantage of the compute resources you have on your machine without getting you stuck in local minima of cost during gradient descent. Here are some hyperparameters related to our word vector space. So remember our word vector space from the slides. Here we had a 3-dimensional word vector space, but I told you at the time that in practice we would have many more dimensions in the real world, and that is exactly what we're doing here. So we are going to have 64 dimensions in our vector space embedding. In case you aren't aware of it, we're going to see this later in the code when we build our model architecture. We're able to use what's called an embedding layer in Keras to create our word vector space as a continuous part of our model. And so unlike if you train your word vector space separately in, say, Word2Vec, this means that the locations of the words in your word vector space not only are convenient for mapping meaning, but also are related to the downstream task that you're performing, in this case, classifying movie reviews. Now, you can't include every unique word in your vector space embedding. And there's a simple reason for this. Imagine if in your training data set, so in our case, 25,000 movie reviews, if we took a word that only occurred once and tried to figure out that word's location in a word vector space, that would be effectively a random location. So we want words to at least have occurred maybe 10, 15, 20 times in our training data in context in order for us to feel confident about that word's location in the word vector space. So by including only the 5,000 most frequently occurring words, we are avoiding those rare words. Another hyperparameter here is number of words to skip. So while we want to avoid rare words, we also typically want to avoid the most commonly occurring words. So these are what are known as stop words. And stop words tend to be filler words. They don't have very much meaning, words like the and an. And so by getting rid of the most common words, we avoid those here. In TensorFlow Keras, not in all automatic differentiation libraries, but in TensorFlow Keras, we do have to have a maximum review length. So all of our movie reviews, if they are shorter than 100 words long, we're going to expand them up to 100 using something called a padding token. If they're longer than 100 words, we're going to clip them down to 100 words. And how we do that padding and truncating is dictated by this parameter here. This could be pre or post. In this case, I'm assuming that the most important information in the movie reviews is at the beginning by setting them both to pre. And then finally, our neural network architecture itself is going to be pretty simple. It's going to have 64 neurons in a single hidden layer, and we're going to drop out 50% of the neurons in that layer to help the network generalize to data that it hasn't seen before. You can just click play on a given code cell to execute it. So in this demo, we're using a pre-made data set, which makes it very easy to work with these movie data. It's this Internet Movie Database data set, so you can just use this load data method to load it in. However, if you're working with your own data set, there are various Keras utilities that will allow you to preprocess your natural language data easily. I recommend looking at the tokenizer class, which may be able to do everything you need in a single line, including what's called tokenizing your words. So taking your language, your long character string of training data, in this case our character strings of movie reviews, and tokenizing it into tokens that represent individual words. You can set your limits on how many unique tokens you want to consider. You can filter out punctuation, which is typically something you want to do. You can convert all of your words to lowercase, which again is something you want to do in most cases, because whether a word is capitalized or not, typically this has a little difference in meaning. And we also want to convert our words to an integer index, and this allows us to make the most of the memory, the RAM that we have on our machine. Some other pre-processing things that I don't have time to go into right now, but you can check out in chapter 11 of my book or in the 5-hour deep learning for natural language processing videos that I have that this code is associated with. But some other pre-processing steps that you might want to consider are, in addition to putting everything into lowercase, removing punctuation, and removing stop words, you might also want to either do something called stemming or lemmatization. So stemming or lemmatization will allow you to group a large number of related words into a single token, so you get more instances of that single word's meaning and context. And then another thing is bigram collocations. So this is saying that if we come across the words New and York as separate tokens next to each other, we want to treat those as a single token, New York. And you might also want to handle trigrams, which would be like handling New York City as a single token instead of 3 separate tokens. So loading our data, very easy, as I said, with this IMDb load data method. It will download it from the cloud. We don't have a huge amount of time to go into the specifics of our data here, but you can see here that there are, if I look at the first 6 reviews in our training data set, so we have 25,000 movie reviews in our training data set, and then 25 labels as to whether that particular movie review is positive or negative. And then we also have 25,000 movie reviews and labels for validating that our model applies well to data that it hasn't seen before. So when we look at the first 6 movie reviews, you can see that they are integers. So each one of these integers represents a particular unique word in our dictionary. We'll look at the natural language in a moment in a couple of cells. So what are the lengths of these? We can see that they have, these are real movie reviews grabbed from the Internet Movie Database. So they just have a random number of tokens in them of unique words. We will set these all to 100 in a moment. And you can also have a look at the labels. So you can see for the first 6 movie reviews in our training data set, the first one is positive, the second and the third are negative, and so on. And as I mentioned, there are 25,000 in both the training and the validation set. So if you want to look at the actual natural language in the movie reviews, I have a couple cells of code here that will allow you to do that. Basically, you download an index that maps the unique token, the unique integers to specific character strings. And so we can use that to recreate the actual natural language in the reviews. So you can see what they look like. So for example, the first movie review, by the time it gets into your goes into your model, it has lots of unknown characters, but you can still see that this is a positive review. Brilliant casting, location, scenery, story direction. Everyone's really suited their part, and so on. And the reason why you see so many unknowns is because we've removed rare words as well as the most common words. If you want to see the whole movie review, these next 2 lines of code allow you to do that. You can read this review, and obviously it is a positive review, and you can confirm that by looking at the label, which when we looked at the labels for the training data set, the first one was indeed a positive movie review. Okay, so pre-processing our data is actually pretty easy. We use the Keras pad sequences pre-processing tool to truncate movie reviews down to length 100 or pad them up with a special padding character up to a length of 100. And so now when we look at our first 6 movie reviews in the training data set, you can see that they all have the same length. This 6th one that was very short now has a bunch of zeros representing padding. So we're padding it up from the short movie review of length 40 or so up to a full length of 100. And you can confirm that now they are in fact length 100. And so a long one that's been truncated looks like this. A short one that has been padded up, it has all these padding characters at the beginning, but then at the end, we do have the movie review in natural language there. All right, as a deep learning practitioner, the most exciting aspect for me is actually designing our neural network architecture. So in Keras, very easy to use the sequential model type to then just add layers sequentially on top of that. Our first hidden layer is that embedding type that I mentioned earlier. This allows us to create a word vector space as a part of our whole model. So that first layer takes in the natural language, those integer tokens that we had here, they get passed in into the first embedding layer, and this is tasked with both creating our word vector space, like this word vector space I showed you in the slides, except in 64 dimensions, and simultaneously, it then outputs the location of a word. So if we had the word king in our data set, there'd be a specific 64 length vector that represents the meaning of that word, and this embedding layer will then output that 64 length vector whenever it comes across the word king. Because these word vectors are two-dimensional, we need to use a flatten layer to quickly flatten it from 2 dimensions down to 1 dimension, because dense layers can only accept one-dimensional inputs. So our second hidden layer is this dense layer. It consists of ReLU neurons, and it allows us to map any of the word vectors, any of the meaningful words here, any of the word vector locations into a particular outcome. So our first hidden layer is tasked with taking the natural language, converting it into a quantitative representation, a location in the word vector space. And then the second hidden layer can grab any particular recombination of those locations and map the meaning of those words to the outcome in this output neuron that outputs a probability as to whether a movie review is a positive review or negative review. So end to end, that's how our model works. In Keras, we're able to have a lot of parameters very quickly, 730,000 trainable parameters in this model. You can go into more detail in my book or videos into what exactly those parameters are. Once we have our model architecture, we compile it. So we have a loss function, an optimizer. In this case, we're using Nesterov adaptive moment gradient descent, which will train very quickly. We use a model checkpoint to save out our model weights after every epoch of training. And then finally, we fit our model. We train it on our training data. So we pass in our training data, the batch size for gradient descent, how many epochs we'd like to train for. Verbosity is set to 1 so that we get these nice outputs as we train. We also pass in our validation data to confirm that our model applies to data that it hasn't seen before. And we have our model checkpoint to save out the model weights after every epoch of training. So how did our model do? Well, it did absolutely train. We can see our loss goes down every epoch on our training data. But on our validation data, we can see that actually it begins overfitting after the first epoch. So our best epoch here was the first, and it had a validation accuracy. Oh, my apologies. The best epoch was the second, and it had a validation accuracy of about 85%. You will get a slightly different answer every time you run it, because the model is initialized with random parameters each time. There's some other cells here below that allow you to evaluate the model, including with an area under the curve of the ROC curve. I'm not going to go into the detail on all of that right now. We only have a couple minutes left. But I have a number of other architectures here in the notebook directory here. We have convolutional architectures. So there's this convolutional sentiment classifier notebook that allows you to now look for triplets, patterns of word vectors, and you can map those patterns of word vectors to the outcome. Is this a positive movie review or a negative movie review? And this model does quite well. So it ends up getting a validation accuracy of 89%, so 5% better than our dense sentiment classifier got. And that covers, I now have a minute and a bit left to cover the last segment of the talk. So we've now talked about our dense and convolutional architectures. The final part, I wanted to introduce recurrent and advanced neural networks. So recurrent neural networks allow you to handle a long sequence of words, specifically long short-term memory units. These are a kind of RNN that allow us to handle up to a sequence of about 100 words in a row and find patterns in there. So our convolutional neural network was able to look for triplets of words. A long short-term memory unit can look for up to a length of 100. And so I have all of these notebooks in here. You can find various variations on these RNNs and LSTMs, including bidirectional LSTMs, which can look for patterns backwards as well as forwards in the natural language data, stacking those LSTMs on top of each other, and even having multiple parallel threads of architectures working together. And in the end, so you can see all of those notebooks, you can examine them yourself in this notebooks directory. So like the LSTM sentiment classifier, bidirectional LSTM classifier, and so on. And you will see that you will get results similar to these kinds of results here. Overall, we find that the multi-convnet architecture performs best. And the reason why our ConvNet architectures perform the best relative to our more sophisticated RNNs and LSTMs is that we didn't have very much training data. So I deliberately picked in this training data set just it's a very small data set so that we could train it in real time as a part of this demo in this short class. But with these short model architectures, it isn't possible to have enough of the nuance for these more sophisticated architectures that can handle, up to 100 length pattern of word meaning. And so, yeah, so if you trained on a larger data set, and in my book, in Deep Learning Illustrated, in chapter 14, I provide you with other data sets that are much, much larger with millions of training data points instead of 25,000. And you can use those to train much more sophisticated architectures using these more complex model architectures. One last thing before we go to the Q&A. Everybody wants to hear about transfer learning and NLP these days, so I just want to quickly go over it. So a couple of years ago, model architectures like ULMFit, Elmo, and BERT burst onto the scene. And these architectures, they are very different from the relatively simple neural networks, deep learning neural networks that I showed you in the last few slides. These architectures take advantage of something called a transformer, which allows the algorithm, the deep learning architecture, to attend to very specific components of your natural language that you're feeding in. And this attentional mechanism is very computationally expensive to train. And so especially for small data sets, these kind of architectures are often going to be overkill, although it might be possible for you to load in, say, BERT, pre-trained on all of the English language available on the internet. And so it has all of this nuanced word vector spaces already built in, and then you can adapt that, you can transfer learn it to your specific task. In my experience using BERT exactly in that way for the movie review sentiment classification that I showed you in today's lecture, the BERT architecture performed comparably to the convolutional neural network architecture that we got with the best. So again, this is something that's probably going to do really well if you have a large data set. There are also smaller versions of BERT that you might want to check out, like Roberta and DistilBERT, that will help you get these model architectures running efficiently in production. And for the real state of the art, you can check out GPT-2. So at talktotransformer.com, it's this very fun website you can go to and type in anything. You can say the DataScienceGO conference is really fun and informative because, and then use complete text to have it automatically generate some more meaning. And as you can see here, the language is quite compelling. The DataScienceGO conference is really fun and informative because we teach important elements of data science with real-world examples and use case. An example of this is our data science repo with 50 projects that are on GitHub and so on. You can see it does an amazing job at creating really relevant language. So these transformers are powerful, but very computationally expensive. For a movie review sentiment analysis task, definitely overkill. And then finally, released just a couple of weeks ago, is this GPT-3 architecture, which is absolutely massive. It is an enormous, enormous model architecture, but it's so specialized and so powerful, so generally applicable, that in many cases you don't need any transfer learning at all for tasks. It simply knows what to do based on the input that you provided, which is really compelling. I recommend you check out that paper and some examples of what it can do. That is the state of the art today. So again, if you want to be able to learn everything that we covered in today's class in an enormous amount of detail, check out my book, Deep Learning Illustrated. There's a 35% off order code there on the slides, although I am pretty sure my publisher gave a 40% off code. So you should be able to access that somewhere. Please do stay in touch. I have tons of amazing things coming out right now. I have a second book coming out that's called Machine Learning Foundations. And so this covers all of the linear algebra, calculus, computer science, statistics, and probability theory that you need to know to be a great machine learning practitioner. And so find out about updates as I release content on that. The best way to stay informed is by going to jonkrohn.com and signing up for my email newsletter. So if you go to my homepage, there is a box right here that you can just provide your email address, and I will only use that. The only thing I will ever do is send you when I have new content ready for you. I will never spam you. And feel free to connect with me on LinkedIn. Just head to my LinkedIn profile and mention that you were in today's lecture so that I kind of can put a face to an experience. I'd love to connect with you there. Definitely my favorite social media platform. I know it's Kirill's favorite too. I also have a YouTube channel. You can get to it here from jonkrohn.com/YouTube. And I'm using this, so for that Machine Learning Foundations book that I am currently writing, the first thing that's going to be coming out is free YouTube videos that cover the content. So we're starting with linear algebra. I'm recording that right now. So maybe as soon as next week, I'll have some of the linear algebra videos out and available on YouTube. And then I also use Twitter. If you like Twitter, I'll be sure to be active on there from time to time as well. Final last thing before we go to Q&A is that I do also have a podcast. Kirill was the guest on an episode recently. Such a funny episode. Episode 3 it was. And if you want to have a laugh and stay up to date on the latest in artificial intelligence machine learning news, I definitely recommend my Artificial Neural Network News Network. All right. Thank you very much. I hope you enjoyed that lecture. Roberto, you got some questions for me from the Q&A?
I sure do. And well, first of all, thank you so much, John, for that great presentation. From what I saw in the chat, everyone was super engaged and following and hanging on to your every word. Well, as you nicely mentioned, I'd like to invite you to a very own DSGO live Q&A. The way it works is the attendees will send questions through the chat. I'll receive them and I'll ask them to you. So attendees, you know what to do. Send your questions through the chat and, well, I'll ask them. We have one question coming in, John. AC Canner asks, if the model runs with random variables each time and provides different validation accuracy, how can we compare different models with each other?
Great question. So that sounds like that's a user who hasn't been dabbling in too much deep learning and gotten used to that reality of working with deep learning models. So if you want to be really rigorous, something that you can do is you could run the model multiple times. So you could run it 5 times, and you'll probably see, unless you start getting into some more exotic model architectures, you'll probably see that you converge upon the same kind of cost and accuracy on your validation data set each of the times that you run it. And so you could then take the average of those runs and compare it to the average of the runs with another model. Now, for the most part, especially, so that would only be, I would say, when you're down the line and you've already tried a lot of different model architectures and you're really trying to refine down to some specific detail on which is the best. Because early on, when you're looking at, let me bring up, is it possible to share my slides still or no? Nice. Yeah. So our producer is bringing a slide back up. I can show you hands-on a good answer here to your question. Basically, yes, perfect. We've got it back up. So on this slide here, where I have this table of results, where the convolutional architectures, we have the first one here with 96.1% accuracy, and this other one here with the 96.2. I will end up, every time I run that architecture, I'll hit about 96.1. It'll round to 96.1. After that, it ends up being random if we go into more precision, but up to 1 decimal place, it will pretty much always round to that same value. So this multi-convnet architecture is always just that little bit better, that 0.1% better than the original convolutional architecture. And things like this simple RNN being much worse, it will always perform much worse than any of the other models here. So I hope that helps answer your question.
Okay, wonderful, wonderful. Thank you so much. We also have a question coming in from Jaya. I hope I'm pronouncing your name correctly. The question is, what is the difference between CNNs and RNNs? For NLP, is it better to use RNNs?
Excellent question. And again, I think the best way to get a full answer and to kind of experience what that's like is to experiment with these model architectures in the notebooks that are available in the GitHub repository that we use today. So the RNNs, specifically the LSTM variety of RNN, is going to give you, in most applications, better results, assuming that you have a large training data set. So the advantage of these LSTMs is that they have a lot of computational complexity. They can handle a lot of nuance. They can handle a sequence of up to 100 words and look for patterns across that long sequence of words. So that's the advantage. But that same advantage is its biggest problem, because it means that if we have a smaller training data set, or if we're solving a relatively simple problem, that sophisticated architecture is going to be way overkill. It's going to take you way longer to train, and in the end, your results might not even perform as well. So on that same slide of results, my best LSTM was this stacked bidirectional LSTM, which had a huge amount of compute associated with it. It got 94.9% accuracy in the area under the curve metric, compared to a 96.1 for the simpler convolutional architecture that took a small fraction of the amount of time to train or to run in production. So the long answer is that it depends on how much training data you have and how complex your task is. The short answer is that assuming you have a lot of training data and you have a lot of time to train a model, the LSTMs, particularly bidirectional LSTMs, should get you the best results, unless you're willing to make the jump to those transformer architectures that I talked about at the very end.
Okay, well, thank you so much. Now, a question coming in from David Wasserman. He asks, what is the next big thing to be tackled by NLP?
David Wasserman, I know you. How's it going, man? Sorry, what was the question? I got distracted by knowing of these 350, 400 people that have been in here. Knowing one of the people surprises me. Sorry, what's David's question?
David's question was, what's the next big thing to be tackled by NLP?
Yeah, so that is a great question. So definitely these transformer architectures and things like GPT-3, which are these absolutely monstrous model architectures, that's where we're going to see the kind of state-of-the-art accuracy for years to come, is in building even more ridiculously large transformer architectures. I think that's going to be happening for the next couple of years. So that's kind of one track where we're worried about having state-of-the-art accuracy. On the other track, for people like me who are building natural language models in production, almost all of the time, it's way more important to me that I can efficiently, quickly provide a result to my users in, say, a web application. So at my current job at Untapped, where I've been chief data scientist for 5 years, we primarily are building models for human resources applications. And so this could involve, for a big corporate client that gets millions of applications a year, they have this database of millions and millions of candidates, and they want to be able to identify who the best from those millions are for a single role that they're currently searching for. So they provide the job description into our web interface, and then they want results immediately. They don't want to wait till tomorrow to get the results because I was using GPT-3 to get 1% more accurate results. Instead, the focus is on building efficient natural language processing algorithms that can instantaneously, in real time, without them having to wait for a second, so sub-second results, look over those million candidates in their pool and give them a result that is almost as good as what we could get with the state-of-the-art and the absolutely monstrous natural language architecture. So alongside that one track where people are going to be using bigger and bigger transformer architectures to get higher accuracy, there's also going to be people coming up with efficient ways of using transformer architectures like Distilbert and Roberta that are smaller and more efficient, as well as making the most of convolutional neural networks and such, as we did in today's class.
Okay, wonderful. Thank you so much. We also now have a question coming in, well, part statement and then a two-part question from Stratos. He begins by saying, Jon, thank you so much for this awesome presentation. Then followed by a two-part question. Do you consider deep learning NLP an extension of traditional NLP or a whole new subject? The second part being, any advice, apart from data sizes, as to when to use traditional and when to go for deep learning?
Yeah, great question. So do you mind repeating the first one for me again?
Sure. Do you consider deep learning NLP an extension of traditional NLP or a whole different subject?
It is an extension, absolutely. So a lot of the ideas related to natural language, so deep learning in the last few years, since about 2014, deep learning has proved to be by far the most efficient, the most accurate way to build natural language processing models. If you now went to a university and you took a natural language processing course, they should spend the vast majority of the time talking about deep learning models. It would be ridiculous to be focusing on, on a lot of other different approaches. And so it isn't that they are separate fields, it's that today, if you want to be working in the field of NLP, you need to know about deep learning, because chances are it's going to be at least one of the approaches that is most relevant to your particular task. And what was the second question?
And the second question was, any advice, apart from data sizes, as to when to use traditional and when to go for deep learning?
Oh yeah, great question. So I don't know why you wouldn't go for deep learning. So even a simple model, like you could, whether you're creating word vectors or there's other kinds of natural language representations that we didn't talk about in today's lecture, like TF-IDF or latent semantic embeddings. So you could use any of those kinds of techniques to create your quantitative representation of meaning, your word vectors, your word embeddings. And then when you're given the choice of, okay, what kind of model do I want to use here? Even I guess it's always worth experimenting with a few different architectures, but at least starting with a simple dense architecture should give you some pretty darn good results, a simple convolutional architecture in the deep learning areas. But you might also want to take, something like XGBoost. Maybe you could get great results using that. I guess my short answer is no, I can't think of specific scenarios where you would definitely want to be using traditional machine learning or deep learning. My recommendation is deep learning is going to probably get you better results and most of the time. But in some situations, actually, you know what? A good reason for why you might want to use something like regression, say, is if it's extremely important for you to be able to explain your model weights. So if for your particular application, the results are you don't want it to be a black box, you don't want it to be contentious. Deep learning, it's going to be complicated. You're going to have lots of complex interactions between a lot of layers, higher order interactions. It's going to be very difficult to explain clearly why it came out with a particular result. And so if it's extremely important that you can say, hey, our model weights this input this much, this other input that much, that is going to severely limit the probably the quality of your model, but a regression model would give you a very clear mapping of weightings to particular impacts.
Okay, wonderful. Thank you so much. I think we have time for one more question. Ilka asks, first states, inspiring talk. Then the question goes, how do you feel about explainability challenges in NLP? For some use cases, for example, analyzing motivation letters for recruitment, the explainability might become increasingly important.
Absolutely. So that follows on great from the points I was just making. There are some situations where it might be contentious or perhaps even against GDPR regulations or something if you're in the EU to use a model in a particular way. And it might require you to use a regression model where you can see the model weights. This is going to severely limit what your model is able to do, but maybe because of the constraints of your particular problem, you're going to be stuck with that. As I explained at Untapped, we're building human resources models. So it is critically important to me and to my clients that our models do not include biases that we don't want to be there. Of course, bias is always said it sounds like a bad word all the time. But of course, all that a model does is comes up with, it identifies trends and it biases to particular kinds of things. So for example, somebody that's a really great software developer, the model should be biased to identify that person as a great fit for a software developer role. Now, there are bad kinds of bias, though, that we want to make sure aren't in the algorithm. We want to make sure that it's not biased against any particular demographic group, for example. And so the way that we design our models at Untapped, we strip anything that could be related to a demographic group out of the input data. And then a patented way that we train our model also makes it impossible for those negative demographic biases to be present. And the most important thing, after you've been careful with the way that you pre-process your model and build your model in a way that you think limits unwanted biases, then of course the final step as a data scientist is to actually test that. So in my case, using a data set of equally qualified men and women or people from different racial ethnicity groups and ensuring that the model scores each of those groups identically. And in fact, in our case, I know that it does. And so there's this trade-off. If you want to be using very sophisticated models like deep learning architectures, there is going to be a black box element, but you can take measures in the way that you pre-process, in the way that you build your model, and in the way that you test your model to confirm that unwanted biases are not present.
Well, I think that's all the time we have for today for this Q&A. It was an amazing way to kickstart DataScienceGO. I hope all of the attendees stay glued to their screens. Thank you once again, John. It was a pleasure hosting you, and I am 100% sure everyone in the audience is super psyched to be following your presentation and following your Q&A. So thank you once again.
My pleasure, Roberto. Thank you for the great audience and your attention spans. As I mentioned on the slides, please stay in touch, add me on LinkedIn, follow me on Twitter, sign up for my email newsletter, most importantly, because that is the way that I can really stay in touch with you. Would love to hear from you individually. Have a great Father's Day, everyone.